Now we'll continue in the Light and Sound unit with Chapter 1, Waves. Section 2 is all about wave properties. The first property we want to discuss is called amplitude. So let's start by drawing a simple wave. First we'll start with the center line. Then we'll add our wave. Amplitude is going to be the maximum distance the wave vibrates from this rest position. So therefore, the larger the amplitude, the taller the wave. So what does a large amplitude mean? Well, large amplitude means more energy. The next wave property is wavelength. These can be measured by measuring the distance between any two adjacent crests in a transverse wave or compressions in a longitudinal wave. Or, if you really wanted to get technical, it could also be done between any two troughs or rarefactions. The last wave property we want to talk about is wave frequency. This is a measurement of the number of waves produced in a given amount of time. For example, we can measure the frequency by counting the number of crests that pass a given point over a certain period of time. Remember, that period of time is what we call a wave period. Frequency is usually measured in what are called hertz. 1 hertz equals 1 wave per second. Now, the higher the frequency, the more energy it carries. So, the more frequent a wave is, the higher the energy it's going to be. Again, remember, we measure a period from crest to crest, or trough to trough. So something that has a lower frequency over that same or longer is going to have a longer period. So the one up top would be considered a high frequency. The one down below then would be low frequency. Now this last slide talks about how we calculate wave speed and wave frequency. The box on the left is an equation for doing the wave speed. The first one shows that the velocity is equal to the frequency times the distance measured, also known as the wavelength. The next two are just variations of that same equation. So again, like we did when we studied oceans, we want to determine what we're solving for. That'll lead us to what equation we need to use. The second box on the right, the frequency equations. It tells us that frequency is equal to number of waves divided by time. Again, the equations that are below it are just variations of that same equation. So when we talk about wave speed, again, simple definition is just the speed at which a wave travels. Again, speed itself is equal to distance divided by time, which is a common equation for things like velocity and speed. Think about your car. We measure that in miles per hour. So the distance then would be miles, the time would be in hours. So talking about the waves like we did in section 1, remember that speed is going to depend on the medium. Okay? The closer the particles are in the medium, actually the faster something tends to move through it. And that's because there's not a lot of space for it to kind of bounce around. So although it might be or might seem a little odd to think about, when the particles are closer together, the waves and the energy actually tend to move through it more quickly. Okay, let's try an example problem. What is the frequency of a wave if it has a speed of 12 centimeters per second and a wavelength of 3 centimeters? So since we're solving for frequency and we've been given a speed or velocity and a wavelength, we want to use the second equation in box 1. Okay, frequency is equal to velocity divided by wavelength. So therefore, we're going to come up with 12, which is our velocity, divided by 3 centimeters as our wavelength. That'll give us a frequency of 4. We'll practice these problems a lot early next week. And make sure you have these notes with you, as you'll certainly want these equations to help you along the way. That concludes section 2.